Good morning, everyone. I'm Pooja Dobhal, Marketing Coordinator at Cengrs, and the moderator for today's session. The webinar title is Phone Penetration Test, Applications and its Interpretation. Welcome to the 7th edition of Cengrs webinar series. Today we'll explore how we can interpret phone penetration test data and its application to geotechnical investigation. We will also go through some case studies for better understanding of its applications in real life projects. I'm honored to introduce our speaker, Mr. Sorabh Gupta, Director of Cengrs, who brings over 20 years of experience in the geotechnical industry. Before we begin, I encourage everyone to participate actively and feel free to drop your comments and questions in the chat box. We'll address them live during the Q&A session. So please do share your thoughts. Now, without much further ado, we'll begin the session. Over to you, sir.
Thank you so much, Pooja. Okay, hello and welcome to our second session on phone penetration testing. I hope some of you had attended our last webinar in which we had covered the basics of CPT. Today, we will try to delve a little deeper into mainly the interpretation of CPT and the application of CPT for practical engineering problems. Once again, as Pooja said, we intend to have these as interactive sessions. So if you have any questions, please keep adding your questions in the chat box. We will finish our presentation and then we'll try to come back and take as many questions as we can. So I'll start. Sorabh Gupta. I'm Director at Cengrs Geotechnica Private Limited in New Delhi. The topic of today's presentation is phone penetration testing, interpretation, and applications. Very quickly, for those of you who don't know about Cengrs, I will begin by why we are called Cengrs. We are asked this question very often. Cengrs is an acronym for Civil Engineers. So C for Civil, ENGRS is for Engineers. The full name of the company is Cengrs Geotechnica Private Limited. We are, I would say, one of the top geotechnical engineering consultancies in the country. We are based in New Delhi, and we are proud to have completed over 6,900 projects in the last 34 years across the Indian subcontinent. So a wealth of information we have in our company. We are a small team of around 150 people, and we are doing around 200 to 300 investigation projects per year. In terms of our service offerings, in short, everything to do with soil and foundations is our forte. So a lot of geotechnical investigations and geophysical surveys, some topo surveys, hydrogeological surveys, and also pile testing and geotechnical consultancy. Of course, you need investigations irrespective of the kind of project which you are building. We are very strong in the energy sector, where I think 70 to 80% of the thermal power plants in the country have been investigated by us. We have also worked a lot on nuclear power plants, solar, wind, building and factories, transport infrastructure, critical bridges, temples like the Ram Mandir temple investigation was by us, and so on and so forth. So pretty much we are excited to apply our knowledge and our expertise to any kind of project that might come up. The company is led by Mr. Sanjay Gupta, who is our managing director, Mr. Ravi Sundaram, who is our technical director, and myself. I'm Sorabh Gupta. All three of us are from IIT Delhi, obviously with different years of graduation, but we are all IIT Delhi alumni, and our mission is to make investigations better. This is a small map of showing our project experience, and we have, I think, one of the largest private databases of geotechnical information in the country. So we took some time last couple of years, and we have mapped all our 6,900 project on Google Earth. So we have this information ready in-house, and this helps us a lot. Every time we take up a new investigation, this database helps us a lot in correlating or doing a desktop study to correlate with what we found earlier versus what we're finding today. So I want to recall. So last time we talked about CPT, we talked about the test equipment and procedures, and we talked about the CPT advantage. For those of you who could not attend last time, I'll just present a few slides uh, just to recap what we had discussed last time, starting with nomenclature. So there's a lot of confusion in nomenclature. We want to clear it up. DCPT is dynamic cone penetration test. This is a very simple test, usually good for very small size projects where or for checking the consistency of fill. SCPT, as we used to call in India, is refers to the static cone penetration test, and typically we used to do SCPT or cone penetration test using mechanical cones. So we prefer now for mechanical cones to use the international nomenclature, which is MCPT, M standing for mechanical cone. ECPT or CPT TE1, this stands for electric cone penetrometer. This is where the measurements of the cone tip resistance, friction ratio, and so on and so forth are with through load transducers which are present in the cone itself. Vis-a-vis a mechanical cone where we used to measure the hydraulic pressures in the hydraulic system, in the hydraulic pushing system, and then thereby we used to interpret the cone tip resistance and friction ratio values. You add pore pressure sensors to an electric cone, and you get something known as a piezo cone. So typically when we talk about electric cone CPT these days, we are referring to piezo cone testing, which is commonly the nomenclature is ECPT or CPTU or ECPTU or PCPT or TE2. So again, our chosen nomenclature to avoid confusion is we like to use CPTU. So U standing for the measurement of pore pressures. And last but not the least, to the piezo cone, if you add geophones and you add the ability to measure seismic wave arrivals, then what you get is you get the seismic cone penetrometer with pore pressure measurements. The nomenclature for this is typically SCPT or SCPTU. So again, in bold, we have chosen to nominate SCPT as the standard terminology for the seismic CPT. This is the piezo cone which we talked about. So the piezo cone is on the top left. This is what the piezo cone looks like. This is you have cones of various sizes which are available, ranging from 2 square centimeter to much larger cones. And but the basic design of the cone remains the same. You have transducers at the cone tip level and along the sleeve to measure the cone tip resistance and the sleeve friction respectively. And also we have a pore pressure measurement. So you have a little filter right behind the cone, which also it's got a pore pressure, a transducer which measures the dynamic pore pressures during the pushing process. There are various kind of pushers available. A pusher is basically the device which is on the ground. Its only function is to provide the thrust or the load required to push the cone directly into the ground. So there are various kind of pusher designs which we had discussed last time. You've got crawler mounted, truck mounted, seabed pushers, so on and so forth. What we are using primarily or largely for investigation jobs is these kind of pushers, which are anchored trailer mounted pushers. It's anchored because you part of the 20-ton resistance comes from the dead weight of the system, and the rest of it comes through augers which are installed in the ground. So maybe typically we use around 6 to 8 augers to provide the uplift resistance. We talked about this last time. This is the CPT advantage, and we went deep into how CPT to begin with is extremely fast. So 30-meter sounding can be completed in just under half an hour. And the time difference between borehole investigation and CPT is tremendous. What you get in a 30-meter borehole, where you get the results in about 15 to 30 days time. In a CPT, you can get the results in just about 4 to 5 hours. So the time difference is tremendous, and that in today's hectic and fast-moving environment, I think CPT gives us the advantage of time, primarily for pre-bid investigations, even for preliminary investigations and detailed investigations. So time saved is money saved. The second advantage is that CPT data is continuous or near continuous. which is extremely powerful as compared to borehole and other traditional methods where typically we have data points every 1.5 to 3 meters interval. CPD is very accurate. It is operator independent. It is company independent. It is, independent of pretty much everything. It's completely digitized. So what you measure is what you get, and there is no human intervention in the entire process of collecting CPT data, which also makes it very accurate. Plus, since the measurements are electronic and the measurements are in situ in the sense that the cone is the measurement of the resistance to the cone penetration is actually at the cone tip level or the cone level. So the results are very accurate. We will see today how the CPT data is very versatile and how it can be used for a variety of geotechnical applications. In terms of depth, a lot of people had issues on the depth. So with the exception of that CPT cannot be used in very hard strata or in rock. If you have a soil site, a regular soil site, typically we are able to push our cones down to around 30, 40 meters easily. If you have very soft clays, like in Kochi and Vizag, we are able to push even deeper to around 70, 80 meters or even 100 meters. Good thumb rule is there's no good way to predict how deep a cone can be pushed. But the good thumb rule is if you don't have too much skin friction, usually you should be able to push a cone down to an N value of around 100, which is good enough for most geotechnical applications. CPT data is extremely reliable. We had seen how if you do two CPTs at the same location, the results are identical or near identical to each other to the extent of 0.1% of full-scale output. We had seen also how the CPT is very modular, so you can add a lot of modules to the CPT. We talked about different modules like adding not just the pore pressure sensor, but also adding the seismics, the geophones. We talked about adding, electrical resistivity measurements, cameras, so on and so forth. It's very safe, clean, and lastly, and definitely not the least in a country like India, it's extremely cost effective. So a lot of people feel that CPD, because of the heavy investment involved and so on and so forth, is very expensive. But actually, as it turns out, we are doing CPTs at roughly the cost of a conventional borehole, sometimes even less than the cost of a conventional borehole. So very powerful technology. This is what the typical CPT data looks like. So you have the cone tip resistance on the left, you have the sleeve friction ratio, and the dynamic pore pressure. And the last or the fifth plot here on the right shows the soil behavior type, which is interpreted based on CPT. We got a question last time as to how we can measure groundwater table with CPT. Again, if you're using a piezo cone and you're measuring dynamic pore pressures, it's fairly straightforward because the dynamic pore pressure, if you're in sands, will quickly dissipate to the hydrostatic pressure level. Very useful to get an accurate measurement of the hydrostatic pressures at the depth of testing or at the depth of interest. If you can driving a cone, since we're measuring in a piezo cone, since we're measuring excess pore pressures when you're driving the cone, obviously, when you drive a cone, you can actually stop the cone at any particular depth, and you can let the dynamic pore pressures dissipate. Naturally, the rate of dissipation of the excess pore pressure would be proportionate to the permeability of the strata surrounding the cone, and this property gives us a very good function. It's known as a dissipation test. Which is a very simple test. You just stop the cone and watch the excess pore pressures dissipate. And this data can be used very effectively for determining the hydraulic properties of the soil, permeability, coefficient of consolidation, T50, and so on and so forth. Again, since it's in situ and there is no disturbance of the soil, aside from pushing a cone through it, the results of dissipation tests will actually give us very good in situ hydraulic parameters as compared to, say, carrying out a permeability test in the lab or in a borehole. A lot of people also used to object to CPTs, saying that if you're doing CPTs alone, you don't get samples for lab testing. So although we don't often recommend carrying out CPTs by themselves, we always prefer, or our recommendation is always to carry out a bouquet of tests at any given point of time, and to design the investigation program as per the technical requirements. So usually we will have boreholes, a few boreholes at least on a site for sampling. But even in the case, for example, if I'm doing a quick pre-bid investigation or a preliminary investigation and I just have a CPT rig at site, it is now possible. We are now collecting piston samples using the CPT apparatus itself. And this is very good because we can actually carry out the CPT, look at the strata on site, decide what is my depth of interest where I need samples, and I can move my rig by another 2-3 meters and then push back and collect uh, actually fairly good quality samples using this kind of a CPT sampler. Lastly, we had talked about the seismic CPT. This is a new addition at Cengrs. We got our seismic cone just earlier this year, and we're having a lot of fun with it because although we have been doing crosshole and downhole seismic and MASW for the last 15 years or so, we borehole geotechnics or borehole seismic was always a fairly expensive and time-consuming and difficult process. This was our experience because you have the cost of drilling the boreholes, you have the time that it takes, the difficulty surrounding actually grouting the boreholes properly as per the ASTM standards. So it is a costly affair. It used to take maybe around 15-20 days before you get a proper shear wave velocity measurement. But with shear wave velocity becoming, more and more becoming a very a preferred geotechnical parameter for analysis, the seismic CPT comes to a rescue because now we have a cone which has got the accelerometers and the geophones built into it. So we can actually push while doing the CPT, we can actually stop the cone, we can impact on the ground, and the seismic waves are captured by the cone, sort of similar to a downhole seismic borehole test. And with this, you get a fairly good, shear wave velocity profile with depth. One thing I want to point out is in our experience, lasting a few months only, what we have observed already is, and which is very encouraging, is that the quality of the seismic data which we get in a seismic CPT is fantastic. Like the seismograms which we get in a seismic CPT are fantastic as compared to what we get from surface geophysics and even from borehole geophysics. So very encouraging technology, and I think going forward we hope to increase the application and understanding of seismic CPTs in the country. So that was a quick recap of what we had discussed last time. I will quickly jump into today. We will talk about CPT interpretation. Very quickly, a quick overview, applications, and I'll show you a few case studies. Starting with the interpretations, as we discussed last time, CPT is very powerful. So, and this is the beauty of the test, right? So you can actually push a cone into the ground, and in about 30 minutes time, you get a wealth of geotechnical information from a single push. So it's possible to understand, we get the state parameters, we get consolidation permeability properties, we get very good strength and stiffness properties, we get very good soil profiling. In fact, CPT is a very good test for quick profiling across a large area. And we also get the OCR and compressibility parameters. And let's look at each of these turn by turn, how these parameters are determined. Before that, this is something which I found, and this is from the Dr. Peter Robertson's handbook on CPT, a very good reference which I would recommend to all of you. So they had these tables, and I found these very interesting. So you see the applicability of SPT interpretations. This is published data, which shows that for different soil types, what is the applicability of SPT interpretations for determining various geotechnical parameters. So a value or number of 1 shows that it is highly applicable, which means that the SPT data is very useful for getting a very good hold of that particular parameter. And a value on the low spectrum, a value of 5, shows that it's not really applicable, and the correlation between SPT and that particular geotechnical parameter is not very strong. So you'll see, for example, that SPT here is fairly good for getting your underlying shear strength parameter, not so good you have an applicability of 3 to 4. For most of the other parameters, your applicability of SPT is roughly 4 to 5, which is very poor. Right? And this is what we are trying to, educate people that geotechnical is not about boreholes, right? So borehole investigations, although we are comfortable with it, all of us are, we are too. It's traditional, it's very conventional. We are used to seeing N values, but we have to keep in mind that borehole investigations have a lot of limitations, technical limitations, not only in terms of execution, but also in terms of interpreting borehole data to get our geotechnical parameters, and also interpreting borehole data to get our foundation analysis parameters. Compare that with the applicability of CPT. And you see here, so the I've superimposed so the numbers in shaded in yellow is the applicability of SPT. So you see here in almost all the cases, the CPT based interpretations are a lot more robust as compared to SPT based interpretations. What that means in plain English is that if I want the undrained shear strength parameter, or if I want the OCR or the stiffness parameter, the modulus, I would rather interpret these parameters from CPT if I have that information rather than getting it from borehole data. Same is the case for bearing capacity, settlement, compaction control, and liquefaction analysis. So you'll see that the applicability of CPT data is a lot higher, and this is published data, as compared to using borehole or SPT data to get foundation analysis parameters. We talked about, and we saw the chart earlier where we had identification of soil type from CPT, and there's a lot of work on this. And I think people like Dr. Peter Robertson and Professor Main, they've really spent years and years, decades almost, developing all these correlations and developing these charts, and we respect them and we are thankful to them for all their efforts. So these are the kind of charts which you have. It's fairly straightforward. So on the y-axis, you have the cone resistance. On the x-axis, you have friction ratio. So, and these are direct measurements which we do in the CPT, right? So if you just plot these direct measurements on this kind of a chart, and depending on where the data plots, it gives you what is known as the soil behavior type, right? So obviously, if you look up on the top left of this chart, as your cone resistance increases with lower friction ratio, typically, these are sands. And as you go on the bottom right of this chart, where you have low cone resistance but a high friction ratio, that's more of, clay kind of soils, because clay will have naturally a lower cone resistance and a higher friction ratio. I want to point out here the difference between soil behavior type and the typical soil classification, which we talk about when we do laboratory testing. These two are similar, but they're not exactly the same. So traditional soil classification, is based on, say, grain size analysis and Atterberg test results and so on and so forth. And that's the unified classification system. In a CPT, because what we are measuring is we are measuring the behavior of the soil as measured by its response to the cone pushing into it. So this is, which is why we don't call it soil classification, we call it soil behavior type. To give you an example, if you have, say, a clay sand, it is possible that the percentage of clay in that mix is fairly low. So if we look at lab testing, we may classify it as a clay sand. But if you look at it in a CPT push, if the behavior of this mix is likely to be controlled by the clay fraction, then a CPT, the SBT would plot somewhere in the clay region, essentially showing that this is, so we talk more in terms of drained and undrained and dilative and contractive behavior when we talk about CPT-based interpretation, which actually makes a lot more sense to me as far as understanding the behavior of soil to foundation stresses is concerned. That said, we have carried out n number of cross correlations on our sites where we have done boreholes and we have done CPTs, and we've made it a practice at Cengrs that we always take data from various tests and we play around with it, we cross correlate, we compare. And what we have found is that the comparison between the CPT and the borehole data in terms of stratigraphy or in terms of soil type is fairly good. So it's since you get a fairly good understanding of profiling in a very limited time and with very good accuracy of as less as 2 centimeters, CPT is a fantastic tool if I just want to go to a large site. We are doing the site right now in Gujarat where it's a huge plot and the customer just wants to understand, what is the lateral variation, what is the stratigraphy across the site before they decide a detailed geotechnical investigation program. So we recommended, and the customer asked us to do a bunch of CPTs all across the site. So we could finish all the CPTs. We could do around 50, 60 CPTs in a matter of days. And very quickly, we got a very good handle on the stratigraphy or the lithology across the entire site. So very powerful, quick test for stratigraphy. I'm not a huge fan of in value, and I think the more years I spend as a practicing geotechnical engineer, the less fond I am of the standard penetration test. And maybe that's a topic for a separate discussion. But still, we, as most geotechnical engineers, we still swear by SPT, and we are still comfortable. I guess comfort inertia is with the standard penetration test. So to solve for this, I think there are now several correlations, including in our Indian standard code, between the cone tip resistance and the SPT value. And we have checked, by the way, and you'll see in the case studies where we have compared the interpreted SPT N60 value from CPT with actual SPT measurements from nearby boreholes, and the match is fantastic. It's also possible to get a fairly good estimate of the soil unit weight from the CPT data. I'm going to jump through these slides. This presentation will be available to you. And if you want to see or get deeper into how these correlations were developed, I would recommend that you go through what I call the CPT Bible, which is essentially a handbook on cone penetration testing by Professor Peter Robertson and Cabal. The latest version, I think, was released just last year, if I'm not mistaken. And it's free to download. You can find it on the internet. And a lot of these correlations we have picked up from his handbook. So I'm not going to go through the equations today, just giving you a quick flavor of what is possible from CPTs. So we get a soil unit weight from CPTs. You can plot this. And again, all of these correlations, I want to point out, over the last 50 plus years, all of these correlations have been cross-correlated with field test data, with trials, with n number of PhD theses have been published on CPT-based correlations, and this has been tried and tested, all across the world where CPTs are being done, and they have been slowly, I think, last 50 plus years, these correlations have also been improved to such a level that now when we are checking these correlations for Indian soil conditions, we are finding them spot on. Again, shear strength parameters from CPT. So your QC versus your shear strength parameter, your EC. You can also pick up, in terms of shear strength parameters, you can pick up, for example, the peak friction angle or the angle of internal friction based on CPT values. You can also get a very good undrained shear strength profile from CPT. And I think this is something which we have used quite a bit. And we have also compared undrained shear strength profiles from CPT versus from boreholes, versus lab testing, that is, versus what we get from, say, field wind shear tests. And I kind of feel that, especially if you have marine clays, the measurement of undrained shear strength or the undrained shear strength profiles which we get from CPT are very, very useful. Relative density of coarse-grained soils. I'm skipping through this just to give you a flavor. So you can plot your relative density in sands. Obviously, you get a very good correlation of relative density with depth. We talked earlier about hydraulic properties of fine-grained soils. So you see how we can get the coefficient of consolidation from the CPT data itself directly. And obviously, as we discussed earlier, it's also possible to stop the cone, carry out a dissipation test, And if you do that, you get an even better or a more refined estimate of coefficient of consolidation and T50 values at that particular depth. If you're working in compressible strata below water table where consolidation and secondary and tertiary settlements are likely, I would highly recommend that we take the time and the effort to stop the cone and carry out a few dissipation tests so we can get very good compressibility parameters in situ. So this is the same thing. The coefficient of permeability also sometimes is very important. These days, we are carrying out lots of projects which require dewatering, or you may have a case where you're designing, say, a dam. So in these kind of applications, the getting a good handle on the actual coefficient of permeability in situ becomes quite critical. We can get that from CPTs. We talked about the seismic CPT, but even if you're doing a regular piezo cone test, the CPT values themselves, much in the same way as we have correlations from SPTN value to shear wave velocity, we also have correlations from CPT data going to shear wave velocity. So this is correlated shear wave velocity, which you can get from regular piezo cone data. Naturally, since we bought the seismic cone, we were very curious to see how our correlations or the correlated shear wave velocity from CPT data matches actual seismic measurements. So we went ahead and we checked, how the correlated value, and we found that the correlated value of shear wave velocity matches what we get from the seismic cone fairly well. We also were very happy to find that the seismic CPT shear wave velocity matches the cross-hole seismic test values very well. The difference, of course, being that cross-hole seismic is not only more expensive and time-consuming, it's also very hard to get clean seismograms in a cross-hole test and to get actual pics of the shear wave velocity arrival. In a seismic CPT, we found that the post-processing of the data it's a breeze as compared to what we had in borehole geotechnics. So that's with CPT interpretations. It's 10:37. I'll talk a little bit about the CPT applications. So we talked previously, we talked about how we can go from CPT data to interpreting the geotechnical parameters. Now, why do we need the geotechnical parameters? The purpose of that is because we want to plug in the geotech parameters and we want to carry out a foundation analysis. Good news is that we don't actually need to go through the intermediary step of determining, so the CE phi and E values. We can actually directly apply the CPT values for foundation design. And there are some very well-established empirical correlations for this. So we'll see how we can do shallow foundation design, including determination of bearing capacity and settlement. We can do deep foundation design, where we can get, the safe pile capacities in vertical and lateral and so on and so forth. We'll see how we can do seismic design, particularly liquefaction susceptibility analysis based on CPT. We'll see how CPT is used in ground improvement control and for design of wick and sand drains. So this is the range of application of CPT results. I want to emphasize that we can actually get, so if you look at the timeline, you can actually do, it's possible for me to do a CPT on site, say today morning at 10 a.m. At 11 a.m., I can just email the results to my office. And at the results, there are so many commercial softwares available for CPT-based design and interpretation. We can actually just upload the data into the software, and at 11:15 a.m., which is 1 hour and 15 minutes from the time we started the test, it is possible for me to get the safe pile capacities right then and there. So very powerful for us. I think in this fast-moving world, this is what we need, is innovations which help us save time and money and help us reach our conclusions faster. We had talked about this earlier. So we had said that, and we are focused on the applicability of the data for determination of geotechnical parameters. There's a similar table given in Professor Robertson's handbook, where he talks about the applicability of CPT data for various design problems. And you see here that the applicability of CPT for different soil types for pile design is 1 to 2, which is very high, which basically means that your CPT data is can be used directly to get a very good estimate of your safe pile capacities. Similarly, it's very good for bearing capacity analysis, which is your shear strength parameter. Very good for bearing capacity analysis, particularly for sands and clays. Maybe not so much for intermediate soils. Extremely good or fairly good for settlement analysis. Extremely good for compaction control in sand, and also extremely good for liquefaction susceptibility analysis. So one by one, we have when we talk about shallow foundation design, obviously, the traditional approaches, we talk about the strength criterion and the settlement criterion. So for strength criterion, which is what we call safe bearing capacity, you can just enter the CPT data directly, and you can get a very good handle on what is my ultimate bearing capacity or my safe bearing capacity for a given foundation size and depth. Similarly, we can input the CPT data, and we can also predict the foundation settlements for open and rough foundations. And the reason we're able to do this is because in situ testing gives us the ability to get the constraint modulus in a fairly accurate form. So we can get settlement predictions. And we did this, when we started with CPT a couple of years ago. We actually, we didn't believe what we read, so we carried out a lot of validation, in-house validation, where we actually carried out, our standard strength and settlement predictions based on borehole data and lab test data. And then we went ahead and we did a CPT at the same site. And then we calculated the open foundation numbers based on CPT as well. And we were quite pleased to see that the results were in very good comparison, to a degree of about maximum about 5% error or so. But then, comparing two different methods is not enough, because what really matters is, what is the real story is how do the soils actually behave when we construct on it. So as a step one, we went ahead on a few sites, and we have some papers which you'll find on a website where we have described this in detail. So this is from one of those papers where we actually did the settlement predictions based on various methods, including SPT and CPT and pressure meter and so on and so forth. Then we actually went ahead and we constructed a 2 meter by 2 meter footing, and we loaded the footing down to, I think it was 600 or 800 tons. And we matched the predicted settlement from CPT versus what the actual observed settlement of the footing on site. And you see the comparison here too, and you see that the comparison is fairly good. The next step, which we are in the process of doing right now, is we are actually doing a lot of investigations for high-rise buildings these days, and we are in the process of monitoring settlements of these buildings during various stages of construction. So hopefully in a couple of months or maybe a year's time, we should also get very good feedback from actual construction sites, which will help us get more confidence in our settlement predictions. Similarly, pile capacities. So incidentally, pile capacity determination from CPT data is very old, and this started from the offshore industry, where naturally, when they have to construct jack-up barges and so on and so forth, they don't have time to do boreholes, and they don't have time to wait for lab testing. So CPTs have been very popular in the offshore industry since the last 50, 60 years. And this is where I think it was born for the offshore industry. So pile capacity determination from CPT is very good. You can get very good quality prediction of pile behavior. And the reason for that, I think, is because if you think about it, a CPT really is a lot like a pile being driven into the ground. So if your test is mimicking the actual construction process, then naturally the prediction from that test will be very robust and should match what we get in the real life scenario. Once again, we did this in-house at Cengrs. We predicted pile capacities based on standard C5 method 2911. We also predicted safe pile capacities based on CPTs done at the same site. And once again, you see that the predicted pile capacities are a very good match. And we did this naturally for several sites and different soil conditions. Uh, and we validated our pile capacity predictions uh, across various geographies and for various soil types as well. So that is, we talked about how CPTs can be used for design of open foundations and for pile capacity design. I want to point out that a lot of projects these days, we are going in for ground improvement. And I think the reason for that is because we've run out of good sites. So now most of the sites which we get for our projects are sites with poor soil conditions where no one thought about constructing, say, maybe 30, 40 years ago. And now we don't have an option. So now we have to construct, in the given situation. So a lot of ground improvement works are happening these days. People are going with vibro stone columns. People are going with various kind of ground improvement techniques, and this is good. But I want to point out, I think CPT has also found its own special place in validating the efficacy of these ground improvement methods. So if you think about, say, if I'm installing stone columns in the ground, my interest is in understanding what are the changes in the stiffness, what are the changes in the strength parameters, what are the changes in the overall permeability of the strata before and after constructing the after before and after actually carrying out the ground improvement process. And as we discussed earlier, we get all these parameters from CPT very quickly and with a lot of accuracy and a single push. So doing CPT before and after ground improvement is actually a very good field validation test as well. So we can do maybe if you have CPT data from uh, the pre-ground improvement on the natural soils, when you carry out, the say if you install stone columns, you can actually bring a CPT rig and you can do a couple of soundings between the columns to quickly check and make sure that we are meeting the design requirements before we stop the ground improvement process. Personally, I feel this is possibly superior to carrying out, say, plate load tests on stone columns or group of columns, because that has got its own limitations. Uh, but maybe a combination of plate load tests and CPTs would make a very good QA/QC program for ground improvement projects. Liquefaction, again, I think this has been a subject of a lot of discussion on many projects, and it's a tricky subject because liquefaction is something which we are still understanding as a fraternity. We have naturally, I think the seminal paper on this is the NCAR paper by Yaud et al., which talks about how the cyclic resistance ratio can be assessed from three different institute tests, primarily the standard penetration test, the cone penetration test, and the shear wave velocity. So the factor of safety, to recap, is very straightforward. Factor of safety for liquefaction susceptibility is essentially the ratio of the cyclic resistance ratio to the cyclic stress ratio. So this is the formula for the cyclic stress ratio. Usually it comes from the PGA value, so you get a fairly good estimate of the CSR value. And for cyclic resistance ratio, we know that we have correlations based on SPT. So I have not presented that. So we also have, in the same paper, we have a graph and a formula for getting our cyclic resistance ratio values from the normalized cone tip resistance. Similarly, we can also determine the cyclic stress ratio the cyclic resistance ratio from the shear wave velocity profile. Question is, I'll go back. The question is, what we have found, and we've done this on several sites, and we have done a lot of literature survey on this as well. So worldwide, the belief is that the CRR value which we get from CPT and shear wave velocity is what should be adopted. The CRR value from SPT is a little coarse and possibly not very reliable, is what I would say. And I think that partly has got to do with the issues with SPT itself, or with doing good SPTs, and partly it's got to do with issues in how the empirical correlation was developed based on SPT, since SPT is non-standard and is done differently across the world. CPT and shear wave velocity, since you have good repeatability of these tests and you have good accuracy, I think CRR values based on CPT and shear wave velocity is what we should trust. Interesting point here is, remember how we talked about the seismic CPT and we said that we get not only the CPT data, we also get the shear wave velocity profile. So if you think about it, this is actually a seismic CPT is actually a very powerful test for a site where we have liquefaction potential. And the reason for that is in a single push and within a matter of, maybe half an hour or 1 hour, we get a wealth of information. So we get the shear wave velocity profile, which can be used for ground amplification studies, for site response studies, and essentially for determining the CSR value. So this is the cyclic demand on the soil. At the same time, we get the cyclic resistance ratio not from one but from two approaches. So you can use the CPT data to get the cyclic resistance ratio, and simultaneously you also have, for exactly the same location, you now have a shear wave velocity profile, which can also be used for double checking the CRR value. So this is great because now, possibly for the first time, we can actually, get a very good handle on not only the cyclic demand, but also the cyclic resistance at our site in a single push. So that's it. So we talked about foundation analysis, we talked about liquefaction analysis. Very quickly, CPT has found a lot of applications for geoenvironmental as well. Possibly not so much in our country yet, but in North America and Europe, this is very popular because the CPT can be actually, you can add a bunch of sensors to the CPT to carry out environmental due diligence, environmental testing as well. This is not my area, so I'm going to just skip through this. These are some studies carried out by Professor Janki for a landfill a site where they carried out CPTs, and they used that information to understand the landfill profile and compare it with borehole data. And again, very good because who wants to go and dig boreholes in landfills and take out samples and take them to the lab. So in heterogeneous formations, I think in situ testing has found a very good application such. And, also because you have a heterogeneous fill typically or a landfill, the shear strength parameters which you get from in situ testing, the profile can also be very useful, whether you're using it for compressibility analysis or for slope stability analysis. You get a very good mobilized shear strength parameter from CPT. So that's it about applications. We have a few minutes, so I will just show you a few actual CPT data which we have. So the first case study, and this is just one slide. This is a project site in Dhulera. We did this with IIT Delhi, where we had some borehole data, and we also have CPT data, and we've compared the two. I just want to point out, so I'm just presenting three plots. The first plot on the left is the SPT N60 versus depth. So I think it's blue. The blue points are the actual measured field SPT values at that site. Now remember, these are N60. So we always, as a practice, whenever we collect SPT values, we always use automatic trip hammers, and we correct the SPT values to 60% ETR by doing an SPT energy measurement at site. So these are N60 values corrected for 60% ETR. And the black line is the interpreted N60 value from CPT data through empirical correlations. And look at how well the N values match what we predicted from CPTs. The second plot is a comparison of the unit weights or the bulk unit weight from CPT, which is the black line, versus the red dots, which is what we got from our Shelby tubes. You will notice here that the two don't really compare well. And our interpretation of that, or our understanding from here, takeaway from here is, I think that's because, very frankly, the unit weights which we get from the so-called undisturbed samples from boreholes, typically not that reliable because of issues in sampling, issues in transport, and issues in measurement itself. uh, but still a fairly good cross correlation. The third one is the friction angle, or angle of internal friction versus depth, what we get from CPT data in sands versus what we get from a drain direct shear test in the lab. Interesting to see again is that the friction angles which we get from in situ testing are slightly higher from what we get in the laboratory. And I think once again, this goes back to the difficulties in sampling in sands and actually getting an intact sample or a good quality sample in sand. And also, limitations in doing lab testing. So eventually, you're trying to get a shear strength behavior by making a small box and doing a box shear test in the lab. So in situ testing gives us very good friction angle values as well. And this matches what we get from real world observations as well. This is a project we did in Baroni. This is a refinery in Bihar. And see how we have compared, not only we've compared first the SPT N60, what we get from the borehole versus what we get from CPT. Again, a fantastic match. We also compared in this project the fines content. So the interpreted fines content, the red line from CPT versus the fines content which we actually got from physical grain size analysis in the lab. Very good match. We also went ahead and we compared the angle of internal friction. So once again, we interpreted the phi value from SPT. We interpreted it, which is the step function with the black line. The red line is the interpreted angle of internal friction from CPT, and the blue dots are the the pink dots are the lab test results. Similarly, we checked the cohesion intercept from the same. Plus, we also interpreted the cohesion intercept from pressure meters, which we did at the same site. And you see how the values match each other quite well. On the lower end of the spectrum, of course, are values which we get from SPT. In situ testing essentially gives you a better or a more robust handle of undrained shear strength determination. This is a plot of the total unit weight, what we get from SPT versus what we get from CPT versus what we get from actual measurements in the laboratory. Very good match. Pre-consolidation pressure, over-consolidation ratio, shear wave velocity, dynamic shear modulus. And remember, we talked about how you can get your cyclic resistance ratio. So here we actually did all three. So we got CRR values from SPT, from CPT, and we had also done a few crossover seismic tests on this site. So we also got CRR values based on shear wave velocity. Compared to the three, we gave more weightage to CPT and shear wave velocity measurements, and we could decide very quickly what is the zone in which liquefaction is probable. This is an example of a dissipation test which we did this is at I think 25-meter depth. This is at a site in Kochi where we had these marine clays down to 50 meters. So we had a lot of fun. We did a lot of dissipation tests in this clay, and we were happy to see how well the test results matched actual expected values. And very clean dissipation test data, which you see here. Similarly, we did dissipation tests in Ludhiana also for another site. The same site, Ludhiana, is So this was an interesting site. By the way, this is a recent project which we did. I just want to take a few minutes. So the customer actually asked us to do around, say, 150 boreholes on this site. They were developing a plant in Ludhiana, a fairly large steel plant. And they asked us, initial ask was to do 150 boreholes across this huge site. It's a greenfield site. The cost of the entire investigation program, say, was X. The time required for the investigation program was working out to be 4 to 5 months because it's huge amount of testing was involved. So we went back to the customer and we sat with them. We understood the design requirements, and we understood that it's not more boreholes which they needed. What they really needed was to understand the stratigraphy across the site, and particularly to understand what is my liquefaction susceptibility zone and what are my pile capacities at this site. So with that understanding, we asked them to maintain their original budget, which they had already accounted for, and we said that instead of doing 150 boreholes, we recommended doing just about 30 to 40 boreholes, and the rest of the test locations we went ahead and we did CPTs. Right? And the result of that was we saved about, I think, 15% in the cost of investigations. So the customer spent less on the investigation program. We saved a lot of time, so we managed to finish the entire work in around a month and a half or 2 months, so which is less than 50% of the time we would have taken with traditional investigations. And third, and possibly most interesting, is with better quality in situ data, we got a much better handle on what is the actual behavior of the soil at the site, CPT being a superior test per se. So we got a very good handle of the liquefaction zones across the site. We could do a 3D mapping, and we could do a more accurate design of our foundation elements and our ground improvement schemes based on this. So the hidden cost here saved for the customer is that they could actually, we could actually justify a lower depth of liquefaction, and that saved them several crores in just the foundation cost alone. So that is really, I think that's the job of geotechnical engineers, is not only to do investigation, but actually to mitigate risk and to do away with conservatism in foundation design and help the customers come up with more efficient and safer and sustainable designs. But so that's I go back. So this is more on the Ludhiana project. So we did a lot of cross correlations, on this project between the borehole data, which was interspersed between the CPT data. We were very encouraged by how well the two test results match in terms of what they give us. So this became a nice trend, and nowadays we are doing CPTs. For example, for high-rise building projects in Gurgaon, we are pushing CPTs down to 30, 40 meters. We're doing fewer boreholes, complemented with other in situ testing like CPTs and pressure meters and cross-hole seismic, and really having a lot of fun getting good quality in situ data to do our designs with. This is an airport project in Jewar in Noida, where again it's a large site. So we did some CPTs to complement our traditional investigation data. These are silo projects. This is one in Sandila. This is one in Gonda. Sonipat. This is a prefabricated. This is a shed actually. Patna, so on and so forth. So most of this, the point of this is, and you can see these slides more carefully in your own time, but the point of this is that CPT is not new anymore. So a lot of people have resistance to, this CPT, thinking it's a new technology. And what we are trying to educate people is it's not new, it's 50 years old. CPT was first, I think, came up in the 1960s is when they started using electric CPTs in the world. In India, of course, it's relatively new, but even in India, so for example, at Cengrs, we have done possibly around 2,000 CPTs in the last 1 year alone. So there's a lot of data which is already available to us, and the data is very encouraging. So this is Unnao, Lakhimpur. These are silo projects again, and that's it. So that's it for today. Thank you so much. Pooja, we can take questions if there are some.
Thank you, sir. Thanks for the presentation. Now let's move on to the Q&A session. Please continue posting your questions in the comment section, and we'll address them one by one.
Please keep them simple.
Okay. So now first question is from Seema. He's asking what is the difference between CPT based classification and regular soil classification?
A good question, Seema. And I think this is a very common confusion as well. So remember, we touched upon this briefly today, where we talked about how it's not CPT-based classification. So when we talk about understanding soils or soil classification based on CPT, we call it soil behavior type. So what we're really concerned about is the behavior of the soil to the cone pushing against it. So largely, the behavior of the soil would be either contracted or dilative. It would either be drained or undrained. So really, that is a behavior, and that behavior depends on the mix of that particular strata. What is the percentage clay and sand and silt, gravel in that strata. So the whereas what we do in a traditional borehole investigation is we take samples and we take them to the lab, and we'll do a bunch of grain size analysis. We'll do index testing, right? Grain size, Atterberg, and so on and so forth. And we use these numbers for classification. So soil classification in the traditional sense is not the same as the soil behavior type, although they are similar in most cases. So if that makes sense.
Second question is from Akshat. Is it better to use CPT for liquefaction analysis, or is it better to do analysis based on the SPT values?
I don't know. Akshat, I might be biased, but so my experience as well as the experience of researchers across the world, I think there was a very good recent publication by Professor Idris from UC Davis as well, which really gets into this, and I found it very interesting. He really gets into this. So they carried out a lot of sensitivity analysis, a lot of studies on sites where they did liquefaction analysis based on SPT and CPT and shape of velocity. And I'll try to find that paper. I don't remember the year of publication, but essentially the conclusion of that entire study was that CPT based liquefaction analysis is a lot more reliable as compared to SPT based analysis.
Next question is from Priya Sharma. What kind of projects or applications should we prefer to go with CPT rather than conventional?
Uh, that's a good question. I would say with so we have to be careful. So I think one, we always say that the geotechnical investigation program should be always should be designed for every project, right? It should not be a tailor-made or a copy-paste job. So it should be designed based on not only what we are building and what are my design requirements, we should also design the investigation program based on what are the anticipated geotechnical challenges at that site. So if I have a rock site where I have shallow outcrop, for example, CPT is not a good fit. It doesn't make sense because you can't do CPTs in rock. The cone will break. So in that case, it's better to go with traditional boreholes. And there are ways and means to improve the borehole information as well, even in rock. And that's a topic of a separate presentation. If I have soils which are fairly compressible soils, I think CPT is always a good idea. That's my view. It depends if I am working increasingly, if I'm working in an area where, say, the project is not as critical, and or if I understand the geology fairly well, in that case, it's okay to go with CPTs alone. However, if we are working in a relatively unknown geology where we don't have prior data on the stratigraphy, or where the project is very critical, we have very high loads, it's always better to go with a bouquet of tests. So I would do boreholes and CPT and pressure meter, dialectic so on and so forth. I don't know, but define that and design that as per the project specific requirements.
Our next question is from Sahil. How can a geotechnical engineer assist in mining industry and meter?
Yeah, Sahil, good question. I think in the mining industry, I think CPTs in India, I agree with you. Unfortunately, I think in the mining industry, we simply don't test enough. I never understood why, but I think we don't test enough. The trend, however, if you look at the trend in the West, I think this is something which will change tremendously, and I think especially for your tailings investigation, I think that is where CPTs are extremely powerful. I think mine tailings is a huge topic by itself. It's a huge vertical by itself. And if you look at, if you just, even if you Google like CPT in mine tailings, you'll find a plethora of information, a plethora of studies and, efforts which are being made in Europe and North America, where they're applying CPTs very effectively for understanding tailings and tailing dams and so on and so forth.
Next question is from Suresh Kumar. How the friction ratio is calculated in a system and what it indicates about the fault state.
So the friction ratio is nothing but the ratio of the sleeve friction and the contact resistance, basically speaking. There are corrections involved which are very minor, but that's primarily what it is. And we talk about friction ratio because when we plot the soil behavior charts, when we plot versus the friction ratio, it's kind of better because it's just easier to visualize where your stratigraphy is. But it's the same thing. It's essentially the measurement is the contact resistance and the sleeve friction.
Next question is from Satyam Verma. How accurate are CPT results?
Satyam, very accurate. Very accurate. I mean, I've been working with boros for so many years, for 20 plus years, and as much as I respect traditional investigations, I think now that we have started doing much more and more of in situ testing, not only CPTs but also pressure meters and seismics and so on and so forth, I think I'm just enthralled by how accurate and how repeatable CPT test data is. And I think that's very important, right? Because if you're a geotechnical designer and if you can really, really rely on your input parameters, and you can have that designer confidence in your input parameters, that the data is not scattering too much unnecessarily. I think that just gives us so much power to really push the envelope of design and optimize our designs, and give the customers better, safer, and more optimized solutions as compared to what we used to. So very accurate, definitely.
Next question is from Neha. How do scientific CPT results compare with the field testing and surface methods for determination of shear wave velocity?
Yeah, Neha, $1 million question. So let's zoom out. So typically, shear wave velocity determination can be done by three or four methods, right? So one, of course, is by using Bender elements in the lab. So that's one way. The second is surface geophysics, like your SASW, MASW. Uh, and the advantage of surface methods is that you don't have to, they're fairly quick, and we do MASW where we want to just cover a lot of area laterally and very quickly because it doesn't require any intrusive investigations. So I think that is the advantage of surface methods. Borehole methods, if I talk about cross-hole seismic tests, I think that is still the gold standard in measurement of shear wave velocity. The reason is because it is only in the cross-hole seismic that you actually put your source and the geophone down the hole, and you directly measure the shear wave velocity of the strata in between the two. The second advantage of borehole methods is that it can be applied for any kind of site, whether it is soil or rock. Right? So that is an advantage of borehole methods. The disadvantage of borehole methods, as I discussed earlier, is it's very costly because you have to make two or three boreholes, case them, grout them. So there's a lot of cost and time involved in preparing for a cross-hole seismic test. Uh, and and the second possibly disadvantage is what we have found practically is that it's fairly hard to, especially if you go very deep, it becomes very difficult to grout the annular space between the casing and the borehole very well. So the quality of seismograms that we get, practically when we do borehole seismics, is not as good as we would like it to be. So there's a lot of manual work in picking, the actual arrival of the shear velocity trains. Uh, what we were happy to see is when we tried the seismic CPT, the limitation of seismic CPT again remains the same as the limitation of CPT, is that since it's a push-in method, you can't apply it for rock of a very hard strata. You can definitely apply it in cases where you have soft or compressible soils, uh, and or just regular soils. The other advantage though is that in seismic CPTs, one, it's very quick because you can get your shear velocity profile in matter of, once again, just an hour or two. It's relatively inexpensive because I don't have to add the cost of preparation of boreholes. And the third advantage is the quality of seismograms. which you get in seismic CPT is fantastic. And I think the reason for that is we have not made any borehole and we have not done any grouting. So we haven't disturbed the strata. We're directly pushing the cone into the ground and we are testing in natural soil. So the quality of the seismic trains is very good. Yeah.
Next question is from Anjana. How do you handle differences between CPT results and other traditional methods like voting? What we do to when the results are different?
Anjana, the nature of our profession, I assume most of us are geotechnical engineers. The nature of geotechnical engineering is that we are very different from say other material sciences, including structural engineering and so on and so forth. Is that we are not dealing with man-made material. We are dealing with natural material. And when we deal with natural material, I think our work is as much art as it is science. You will never have perfect results. We will never have enough data points because in the end you are only you are all you have is a few pinpricks in a tremendous volume of heterogeneous material, which is a very complex material. And the reason I say this is because I think as geotech engineers, we are used to getting data from different sources, which may not always match perfectly. And this is where our judgment comes into play. That said, that's my background. So my answer to you is good engineering judgment, and there is no substitute for experience and good engineering judgment. When you get data from different test results, you have to use your knowledge and you have to use your intelligence to really understand how to pick your design profile. That said, I think in terms of reliance on different test methods, I like to rely on in situ test methods wherever they are available. So if I am given a report, I usually first I look at the CPT and pressure meter data or the cross-source seismic test data. I look at that first, and then I go back and look at what I get from boreholes as a mostly to corroborate or to cross correlate what my in situ testing is telling me.
Last question from Sagar. How do we decide the scope of geotechnical investigations for our project?
Yeah, we get this question quite a bit, Kapil. So we, so again, if you saw, I think our earlier presentation, we always said that the scope has to be defined. I think what more and more what we are finding on projects is that we are finding the investigation program scope to be just a copy paste job. There's a BOQ which was applied on the previous project, and normally that BOQ is copy and pasted, and it is directly presented as a scope for the next project, irrespective of the fact that the project might be in a completely different geology with completely different geotechnical challenges, and we could be building something completely different. So we don't subscribe to this, this manner of defining the investigation program. We do always insist that spend the time, invest the time and effort when you have a project in doing a desktop study in looking at what is the prior experience in this area, what do our neighbors, what have they experienced, what kind of foundation systems are implemented, walk the site, see if you see any signs of distress, and think it through, spend a lot of time and effort thinking about whether we want to do a single stage investigation or multiple stage investigation, and what we should do, and what are the parameters we want to target, and what are we trying to get out of our investigation program. So I think this is invaluable, right? So versus what we are typically doing in our country is we do a copy paste job. After 2 months, you get a report, and then we react. Either we don't trust the report because the data is unreliable and we discard it and we do another investigation, or we get a report and then suddenly we find, oh, okay, so we have a liquefaction problem here. Oh, so now then we do our costing and we say, oh, the cost is going very high, so let's go back and let's carry out some additional tests. So you waste another 2 months, and which is time lost, money lost. So it is definitely worth thinking your project through right in the beginning, take advantage of prior experiences and design it. I'm showing this slide here because at Cengrs, we got a request from a lot of people. So for the last, I think, 2 years, we have an offer and this is our give back to the fraternity as well, that if you have a project and you need guidance on your defining your geotechnical investigation scope, all we ask is that just email us your project location, site photographs, structural details, and any available data that you have. And our commitment is that we will help you, we'll consult with you, and we'll help you develop your GTI scope, and we'll give you a BOQ which you can work with. And this is completely free of cost. There are no strings attached. You need not even engage us for the investigation. We don't care. So this is, we have a team, uh, in-house team which we have kept. Think of it as CSR, which only does this. So they only do the scope definition for people who need it. So if you need something, please do get in touch with us.
Thank you, sir, for addressing these questions with such clarity and expertise. And as we approach the end of today's webinar, I would like to thank all of our attendees for joining us. Their participation and engagement have made this session truly valuable. And if you have any further questions or would like to continue the conversation, please feel free to reach out us at our social media handles or via mail. Also excited to announce our next webinar, which will be on 21st December, and in that we will explore our file integration test. So please don't miss it. Once again, thank you, sir. Thank you all the attendees for attending us today's webinar, and we really look forward to seeing you at our future webinar. Have a wonderful day. Thank you.
Okay. Thank you, Pooja. Thank you, everyone. Have a nice day. Bye bye.